All right, one more thing we need to say about this chase problem before we try another one has to do with this graph. We were saying that the cop has to eventually go faster than the speeder to catch the speeder. So there's one more thing we need to look at on this graph, and that would be the distance traveled. So we found that the catch time was 16.67 seconds, and that the speeder is going 25 meters per second the whole way. So the area of this rectangle is the distance traveled by the speeder at 416.7 meters. It's got to be the same area as the blue triangle. Now, what do you think that final velocity is for the cop? We could use the acceleration formula. Plug in the values. We get 50 meters per second. Just by inspection on the graph, that looks right. We have symmetry here. Well, this is a theoretical situation. Cops won't pull a speeder over when the cop is going twice as fast as the speeder. So in real life, things will work out differently. Let's modify the problem. The speeder goes by, but the cop doesn't start chasing for 5 seconds. Now what do? One thing you can do is to start the problem when the cop starts the chase. By that time, the speeder is 125 meters down the track. When we set up the equation, we have to remember that this is the time from when the cop starts the chase. Boy, that one little change, and now we have to use the quadratic. Now that's the time while the cop is chasing. Plug it back into either side on the equation, and we get 642 meters. Let's plot the graphs. Now pause the video and try the graphs first. I'm going to do the graphs first from when the cop starts the chase. When the cop starts, the speeder is already 125 meters down the road, moving forward at a constant velocity. The cop chases from an initial velocity of 0, so the initial slope should be 0. And that's where the catch occurs. Make sure you label each. The speeder is traveling at a constant 25 meters per second. The cop starts from rest. I know what you're thinking. It's going to be the same graph as before. But wait a second. The areas under these graphs won't be equal because this graph doesn't include the 125 meter head start that the speeder had. Because the cop waited 5 seconds, the speeder got ahead, and now he's got to catch up even more distance. So the area of the blue triangle is how far the cop traveled, and the red rectangle is the distance traveled by the speeder while being chased. That's a final minus an initial. To get the final distance of the speeder, we take this area and add the initial distance of 125 meters. Now, how would these graphs change if we wanted to graph it from when the speeder passed the tree? You pause the video, try to make your graphs first. Now the speeder starts at a position of 0, moving forward at a constant velocity, but the cop doesn't start for 5 seconds. And there's the catch. It's really the same graph that we had before. It's just moved over. This is where we had our axis before with 0 time. How about the velocity graph? The speeder's still doing 25 meters per second from the start, but the cop doesn't start for 5 seconds. Now from here, you get to see the whole picture. Now you can see the 125 meter head start that the speeder had. The area of the blue triangle has to equal the area of this red rectangle. What would the formulas look like if we did start from 0 seconds? You'd still have to say that they're going to be at the same position in the same time. Now you have to be careful because those times are not the same. That's the time that the cop has been traveling for. That's the time from the beginning. So we have to subtract 5 seconds because the cop is traveling for 5 seconds less. Expand the squared term, plug in all the values, distribute. Now we're ready for the quadratic. Do the quadratic, and you get 25.69 seconds, and that's from when the speeder passed the tree. Plug it in on the side with the speeder, and you get 642 meters. Plug it in on the side with the cop, and the formula takes away the 5 seconds because the cop sat there for that long. you still get 642 meters. Personally, I think the Head Start method is a heck of a lot easier than all this. Let's do one more. The red car is going to the right at 20 meters per second. The blue car is going to the left at 15 meters per second. The blue car starts at a distance of 500 meters to the right. Where will the catch occur? Again, we start out by saying the final position will be the same. We only have VIT for the left, but we have VIT plus an initial position for the car on the right. Okay, I've made a classic mistake. Can you find it? If 20 meters per second is to the right and the 15 meters per second is to the left, they both can't have the same sign. 15 meters per second is going to be negative 14.29 seconds. Plug it back in on either side, and you get 285.7 meters where the collision occurs. I think that makes sense. This has to be more than halfway because it's going faster than the blue car is coming back. You knew these were coming. Go ahead, take a shot at it. Yeah, the red car starts off at 0 distance, moving forward at 20 meters per second. The blue car has to start off at 500 meters. It's going backwards though, at 15 meters per second. That's a little slower than the red car is moving forwards. The slopes can't be the same. The red is more steep than the blue. And the velocity is constant at 20 meters per second for the red car. And the blue has to be negative 15 meters per second, constant. Now, what about those distances traveled according to these velocity graphs? We found the time before to be 14.29 seconds. If we take that time and multiply by that velocity of 20, we get 285.7 meters. That's how far the red car has traveled to the collision. Take the same time, multiply by negative 15, and you get 214.3 meters, but that's negative. This means backwards. And that's how far the blue car has gone backwards to the collision. Need more review? Go to the chapter notes. Section 4.1, chase problems. Here's the cop and the speeder. Same graphs we just did, with a discussion. What happens if the cop waits 5 seconds? Here it all is, including an analysis on the Head Start method versus the Delta T method. In the practice problems packets, you're going to find a summary of chase problems, but you're going to find a whole bunch of problems for you to try. Lots of problems. I have the answers showing some of the work.